Hello, everybody. Hello, all 9 people. We have more people filing in, but Shink. How's my Friday morning going? It's been all right. It's a nice fall day out. Got a better view than I would if we were in the lecture hall. How about you? Yeah, the weather outside. Yeah, I think September is the best in Edmonton, personally. Okay. Cool. All right, up to 15% or 15. That's like what, 25% of the class? 15 students. We have, oh yeah, you're right. We have closer to 90 people in the class. I can't do math in my head anymore. This is why I'm a computing science professor. I have computers do that for me. No, so it is not 25%. It is. It's all right. I'll have a computer do it for me. 16.6 repeated percent. Perfect. It's actually not true though. When it was the old ad drop deadline, we were down to like 86, 87, but I don't know if more people joined after. Just as a quick note of warning, if you're somehow in this chat and you haven't done the PQs from Wednesday, I would do those as quickly as you can because I'll be closing those in just a few minutes. Very little about the other classes that occur here. This is only my beginning of my 3rd year here as a professor, and I've only taught this in a grad class. So I've taught a lot of this in a grad class, in my grad class. So. All right, is she here? Thanks. I did lecture at my old university. I mean, specifically here, so I don't know a lot of the the classes here specifically, but thank you. That's strange. Natural paths. Let's see what we got to with our natural paths forms. It's like 72. It's not terrible. See, some people are deciding to just hope that I only use the first one for marking. Unfortunately, that's not what I'm going to do per what I said in the class, in lecture. Oh. Okay, so about 30. So now we're about a third. This time I did do math correctly. Let's give people about another minute just because this is a slightly weirder thing. And then we'll go ahead and get started. Okay, let's go ahead and just share my full screen. And here we go. Cool. So today we are going to be covering A-star pathfinding. Finally, you'll get to all fix the behavior of Pac-Man, who you were all so worried, or not all of you, but many of you were so worried about the behavior that Pac-Man was displaying in this last assignment. This was done intentionally, it was intentionally bad, such that you would then be motivated to fix it in this one. You cannot get rid of the watermarks on the Zoom video. It's just a fun UAlberta security thing. I could instead change it to require a password or require a waiting room where it'd have to individually let people in. This is, I think, the best solution, as much as it is not particularly appealing visually. Again, remember, you'll get the slides after this. Okay, so some quick announcements before we go. Obviously, I'm going to be paying better attention to the Zoom chat because it's literally all I can see right now. But yeah, homework 1 is due tonight, 11:55 p.m. Yes, there is a 23-hour grace period, but there's going to be far reduced TA/instructor and me response times on homework 1 questions. So if you were thinking like, if you were thinking that, you know, you'll be able to post on the Discord at, I don't know, 1 a.m. and I'll respond just as fast as I have been this week. No, I'm sorry. I'm generally going to stop responding to most homework 1 questions after that hit point. So I wouldn't wait. I would try to get it done as quickly as you can. There is, speaking of, an office hour directly after this. Now, we had a problem. Both myself and the TA had problems in terms of the Google Meet link we were using. And so we've made a new one that should be better. That's now on the syllabus and that's now right there. I'll also post it in the Discord once it starts, basically right after the end of this class, or end of this lecture, this weird online lecture, right in a class. Homework 2 has been released. It was released yesterday, and it'll be due at 11:55 p.m. on October 4th. Now you might be going, oh, wow, I have so much time. Homework 2 is harder. I was chatting with one of the students who showed up for the very, very long lab session yesterday. And they were saying, you know, the main part of the assignment only took them 30 minutes and the rest took them like a day. That's a slightly weird balance, right? But for the future, it's going to be a more even split between the amount of time it would take for the main part of the assignment and the extra credit. So you should expect homework 2 to take you longer than homework 1 did. So I wouldn't wait to get started on that. There will be a helper video and other things and et cetera, et cetera. We'll figure it out exactly how I can help, if we can have an in-person thing, whatever. But regardless, you know, start early. 90% of you completed Monday's participation questions, which is much better than only about 72 out of the 90 something of you, or 90, 80, maybe 80 something, maybe up to 90 of you that completed Wednesdays. Which is a shame. I think it's because Monday's participation question was literally just 2 multiple choice questions. And that's a lot easier to get you all to do. Even then, I don't know. Anyway, I can't just do multiple choice questions, unfortunately. I do need to get other kinds of feedback from you. Quiz one, real quiz one, will be on space representations and path planning, and it will be next Friday. This is going to cover all the lecture material through next Wednesday, but it's going to be focused on everything until next Monday. So just basically one more lecture's worth of material that is really going to be on, and then Wednesday might be a little bit of a touch on things. What I think we're going to be doing is Monday we'll be watching a lecture, and I'll be giving basically commentary on a lecture on a particular game's spatial system and path planning approach. And then on Wednesday, I'll talk about a very specific a pathing approach. It's not really pathing. Anyway, that's roughly the plan. There will be another practice quiz today. We'll just be doing it in this weird online format. Okay, also I thought it'd just be fun to mention, since Deltarune Chapter 2 releases today, that hey, this is a series that uses grids. If you're not familiar with, I don't know if kids these days hate Undertale or whatever, and Deltarune as well, but you can clearly see it just from this screenshot, right? If you've come to recognize how grids work, that this is very clearly a layout that is on a grid. Now, this is primarily because the original game was made in Game Maker. I think that they've since ported it to other things, but they're still using this sort of grid representation. Okay, quizzes. I thought I'd give a little bit of a rundown on, hey, what the heck are quizzes? Because we haven't had like a real one, but hopefully I've given you enough of an idea with these various practice quizzes that you can mostly see what's happening. So there's going to be a number of fill in the blank style questions. So the way this works is I'm going to say, basically, like, here's an environment, tell me where there's obstacles, or here's a question, pick one from these set of options for each of these blanks, things like that. And that means that each of you is going to be creating your own questions. This should be fairly straightforward. There's no trick to these things where it's just like, make a decision about what your question looks like. That's actually going to be like a question. You'll get points for doing it correctly, like not mucking up and putting something I said, don't put this here somewhere. But there's no trick to them. You just do them, and then you sort of use those as the basis for future questions. There will be a combination of multiple choice and short answer. It's much more short answer and much less multiple choice, but there'll be a couple. Questions will depend on each other, which is partially this fill in the blanks thing, but also for other stuff. So I might say, okay, you suggested you choose to use this spatial representation in this question. Well, what if we took your solution from that question and we tried to adapt it to this new environment? What would that look like? Things like that. There's no lecture on quiz days. So on Friday, even though we are technically back in person next week, again, you can always show up hybrid or through the online Zoom meeting. On Friday, there will not be a lecture. What that means is I'm just going to show up in the classroom, because technically I'm supposed to, I think. And I'm just going to be there. If you want to be there as well and start doing the quiz there, you're welcome to. But also, I will just sit on the Zoom call as well. I'm not going to release the recording. That'd be weird. So if you want to ask me questions, that's fine. I'm just not going to let anybody like share their screen or anything, because, again, don't give away answers. The quizzes are only designed to take 1 hour, but you are going to have 48 hours to complete it from when it's released at 11 a.m. next Friday. Okay, so we have a lot of time. Most people should not take that much time, but also I wouldn't recommend waiting until the last possible minute to do it. There's also on the Discord, there's a quiz discussion channel, so you can ask questions about the quizzes there. But again, don't ask questions that reveal answers. If you have a question that you think is going to reveal an answer, send it to me over email or ask me in person. Quiz 2 will be 2 weeks after quiz 1, covering pathing and decision making. Cool. Any questions on quizzes? Basic notion of this working. So I don't have any nodding heads. I miss my nodding heads, people who just nod. Okay, I appreciate it. Okay, the thumbs up is a good alternative. Thank you. That'll work. Okay, so real quick, I'm actually going to stop this slideshow if I can figure out again how I'm supposed to do that. Here we go. I helped about 1/10 of the class, about 9 people, yesterday during the long lab session, which was extremely long and tiring. But there was a couple of people who asked questions which were worrying to me in terms of basic concepts you're going to need to understand for the class. So one of those is vector data. Now we're mostly going to be about to be past your need to understand vector data, but you should understand how like
polygons and points and lines and vectors work. So I've just included this like extremely simple, very short web page on explaining how vectors work. Like a big question that worried me that somebody asked is like, when we're talking about the points in a polygon, do we talk about all the points in a polygon or just the corners? Like, no, there are only the corners. The only corners exist in polygons. None of these lines are points, according to this definition, right? So this is an important thing. If you do not have a background in geometry, that's the right one, yeah? Yeah, that's the right one. I would recommend reviewing this information. It's really short. Another thing that's been worrying me is people don't seem to have an understanding, or some people don't seem to have an understanding of like classes and objects and how you can call different things. This is particularly coming up with people asking questions about polygons. And also there's some questions about how like lists work and stuff like that. So this is a tutorial on C#, and I'd recommend reviewing it if you're feeling like, I don't know how to do any of this. Again, per the syllabus, you need to have some basic understanding in like a related language to be able to do well in this class. But yeah, those are two things. I do not have the time to go deep on these topics, but if you find you need help one-on-one, I can talk to you about it, but here's some resources to be able to help you potentially. Okay, so quick review on what we've done so far, literally on what we've done so far on these topics. We've talked about 3 ways to represent space, right? We talked about grids, path networks, and nav meshes. We talked about greedy path planning, and we talked about 3 ways to post-process path movement. That was just on Wednesday's lecture, path smoothing, steering, and formations. Okay, this is it. This is the majority of the content that we've covered so far that's going to be on quiz 1, along with today's lecture and Monday's lecture. So graphs. Graphs are interesting. You might be saying, wait, hold on. None of these things that you just mentioned have to do with graphs. So actually they all have to do with graphs. So it's a helpful thing to be able to imagine all 3 of these different spatial representations as a single kind of spatial representation. And we're going to think of that in terms of a graph because they're all graphs secretly. Watch out. The basic notion here is that we're going to have nodes, which are a basic unit for the graph representation. This is like points in space. And then we have, sometimes they're called vertexes or vertices. And then we have edges, which are links between nodes. They can have a weight on the edge to represent the cost of travel. So a graph, all of our spatial representations so far can be decomposed to be graphs, like how a grid can be a graph, right? It's just this very dense graph. The node is every midpoint of every grid cell, and the edges are the lines that we can travel to go between grid cells. Similarly, obviously path networks are graphs, like just look at them, right? Like they're the most graphy of the 3. And then nav meshes are of course graphs because we want to actually extract just a path network again from our nav mesh to say, how do we move between them? Okay. So at first it might be like, wait, why are we talking about these things? All as graphs, like what does that matter? Well, it's helpful to have some sort of standard general way that we can talk about these things to compare between different spatial representations. For example, what if I want to talk about how much a particular spatial representation is going to take up in memory, right? If we can compare them in terms of the same graph representation of nodes and edges, it's a really easy thing to say, hey, which one has the most nodes and edges? Simple, right? Problem. What I just said. It allows us also to discuss different search approaches without worrying about the exact spatial representation. So we can talk generally about like, what are the different kinds of ways that we can path plan, that we can move, that we can search through the space without having to worry about exactly what the space looks like. Okay, so let's talk about this greedy path planning algorithm that we mentioned a while back. I think just on Monday, yes, last Friday, a week ago, geez. So what we want to do is, again, we want to find a path from start to the goal node. That's our goal. That's the thing that we're trying to achieve with this algorithm. The first thing we want to do is want to add the neighbors of the current node to some open set of list. This is basically saying, hey, these are the locations we can get, right? So like from where we're at, imagine we're at A, we can say, hey, where can we get from here? Oh, we can get from B and D. Then we want to pick our next current node from the open set. Now, the important thing that a lot of students have trouble understanding here is when we're saying pick the next current node, we don't mean that we're moving the agent there. You can think of it as sort of like simulating what would happen if we moved the agent there, like what is possible if we move the agent there. But we're not literally like moving the visual representation of the agent anywhere. Then if our next node is the goal, we want to backtrack to the start of the path. And if it's not, then we keep on going back up to 1. Okay, so question, and I'd love if I could get some people talking in the chat. We'll see. Beyond improving the heuristic, how can we improve the greedy pathing algorithm? Right? Maybe this is not an example that's like super. If you'd like to chat on the Discord instead, you can do that while you're watching that. But maybe this is not a super helpful example here. But like imagine there was an obstacle cutting off this section here. What could we do to make pathing better? Like at least an answer. Have some info on the difficulty of traveling to each node. So sure, I mean, with a grid, right, we just know that every grid cell is a 1 unit. Unless you're talking about tracking how far we've gone. Is that maybe what you're suggesting? How long it took to get to each node. So Victor, shortest distance or lowest cost of travel, that would just be a heuristic, right? We've already talked about we're going to use a heuristic to be able to figure out which node we select next. So that's not going to be changing anything over greedy. So the searching the grid before actually going is what all of these algorithms are doing. So that's not a change over the greedy algorithm. It's also searching the grid. The choice is, the difference is how, right? The distinction is how is it searching the grid? Is it searching the grid in the most effective way to find the shortest path? So Marcelo suggests detecting obstacles before planning the path. So that could work, but that would be a change of the heuristic, not the algorithm, right? Because we could use a heuristic, we could increase the heuristic weight if we had obstacles in between ourselves and the goal. Adrian suggests prioritizing nodes that bring us closer to the destination node before looking at others. So again, that's just using a heuristic. Use something like epsilon greedy. So I wouldn't recommend using something like epsilon greedy because we're in a discrete environment, a non-stochastic environment. I also wouldn't search all nodes instead of just the closest node. That would be like a depth first or a breadth first search. That's gonna be a lot slower. Okay, so I think that you all are having some trouble conceptualizing, right, the difference between changing a heuristic and changing the algorithm. So let me just move forward and let's look at it. So let's talk about A star, right? So this is going to be a distinct algorithm, not a change in heuristic. We use the same heuristics between greedy and A star. But this is a change in how we are going to be doing this path planning process. So what we're going to do is we're going to change it, this path planning process. So nodes are going to have 2 costs, not just the 1 cost of the heuristic. So in addition to the H score, which is the heuristic, the estimated cost of getting from here to the goal, right? Which could include things like, if there's obstacles in between, it's a straight line distance, things like this. These things are the things you're saying. That's where the H score goes. But the G score is the new thing here. So this is going to be a tracker of the cost from getting from the start to here, to where we are right now in the path planning process in the search through these nodes. That's the distinction. And then we're actually going to be using the F score, a combination, just a straight up addition between these two things, to be able to figure out which node are we going to select next, which means that we're going to be doing a combination of saying like, okay, we want the nodes that's going to get us the goal the soonest, but we don't want to make sure that we're sort of like caught in a dead end, which is what the G score is going to give us. So A star is therefore, because of this combination of these two things, going to do a better job than this. It doesn't have to search all the way to the sort of bottom of this upside down C before it's able to figure out its way to the goal. And we will pick which node to choose next based on these 2 scores, as I mentioned. Okay, in addition, a couple other changes. We're not going to just have an open set, so a list of nodes saying these are the places we can get. Instead, we're also going to have a closed set. How does checking the cost from getting from start to here help? Is H just the direct distance from that node to the end goal? So, okay, D says, how does checking the cost from getting from start to here help? It helps because we don't get into a situation. So for example, with greedy, right? Let's talk about the distinction between A star and greedy for this setup. I hope everybody can see my mouse. So as we can see right here, right? If this was greedy search, with greedy path plan, with greedy search, we would just straight line, we'd put all of these nodes all along here to this point right here to get to this node, right? And only then would we start expanding. We would have to expand this whole section, this whole area. We have to search this whole area before we figured out this path. Instead of that, D, what we can do is we can just say, okay, for A star, we're going to do a weighted combination of both how close it is and how far we have to travel, which means we're going to search this whole region all at the same time. And we're going to end up finding this goal much, much sooner. Does that make sense, D? Cool. And then Naheen says, is H just the direct distance from that node to the end goal? So the heuristic is variable, Naheen. It's not stuck. It's not just one thing. It could be the direct distance from that node to the end goal, but it could also be all kinds of other things. It could instead be, a notion of the distance plus if there's an obstacle next to you. It could be a notion of the distance plus, I don't know, maybe you want to bias the distance in some way. So it's a distance that's less in the X dimension and more in the Y dimension, whatever it is, right? It could be lots and lots of different things. It's just an estimate of how much longer it's going to take to get to the goal. Does that make sense, Naheen? Cool. Okay, so let's keep moving. So the other difference between A star and sort of greedy path planning is that we won't just have an open set. We're also going to have what's called a closed set, which is a sort of nodes that we've already evaluated. And this is really powerful because it means that we're not going to get stuck in a loop of just checking the same nodes over and over and over again. An open set is also, another difference, going to be a priority queue. So it's not just like a big list. It's a priority queue, which means that as soon as we discover a better node, so in terms of this F score, this combination of G, the distance we've gone, and H, our estimate, our heuristic of how much further we have to go, we can immediately pick that as our next node. Okay. If you're not familiar with priority queues, I don't have the time to sort of dig into them, but regardless, high level, they are a data structure, which is always going to give us the thing which has the minimum weight, the minimum cost associated with it first in that data structure. So if we ever ask for a thing from this data structure, it will give us the thing with minimum cost. Right, which is what I just said. Sometimes I should look at the thing just after what I'm saying. Okay. Here's the pseudocode for A star. This is by far the most complex pseudocode that we've talked about in the class. And it's going to be about the level of complexity of the assignments going forward about. FSM goes a little bit down, clustering hits about this level again, and GA is also hit about this level again. So let's talk through it, right? I'm going to walk you through this line by line. So first, we're going to start by putting our start node. So this is the node that we're starting on, whether that's a grid cell, the middle of a grid cell, or a path network node, to our open set, because it's saying, hey, we can get here because we're already here. Then, while our open set is not empty, AKA we have places we can still go, because it's possible that we could get into a situation where it's just not possible to move to where we're trying to go to. So while our open set is not empty, we have still places we can potentially get to. We want to pop our open set, which again, pop is the thing that's going to grab the minimum cost thing from our priority queue. So it's going to return the minimum cost thing, which is current. Now, because the open set was just our start node, this first one has to be our start node, right? In future iterations, it'll be other things. But for now, it's just the start node. If current is the goal, which would be weird, right? Imagine if we just like had Pacman click exactly the location of Pacman was on, then we could just reconstruct the path, right? Now, later on, we will find the goal this way. Otherwise, so if that isn't the case, we don't just return, we're going to add current to our closed set. This is going to ensure that we're never going to go to current again. We're not going to go to this node, whether this node's value is, this particular position, we're never going to check that one again. Then for each neighbor of current, so that's all of the nearby. So for a grid, right, it's the cells above, below, to the left, and to the right, right? We're going to check and see, hey, if that neighbor is in the closed set, then we just continue. Continue is a way of saying go to the next iteration. So go check the next neighbor, right? So this is the thing that's ensuring that we're never going to check something that's in our closed set again, okay? Then what we want to do is we want to take our G-score and we want to set that equal to the current G-score plus the distance from current to the neighbor. So this is a way of figuring out, hey, how much work, how much distance do we have to travel to get to this neighbor? That's its G-score. If the neighbor is not in the open set, right, which is the open set, which is the priority queue, which is the way of tracking what can we get to, we want to just simply add our neighbor to our open set, no problem. But if the G-score for this neighbor is less than the neighbor that's in the open set, then we want to replace it. Now, this is a little bit complicated to maybe think through, but basically the idea is if we found two different ways, two different paths for getting to the same node, and we just now, second, found a path which was shorter to get to this node, then we want to replace it. Okay? Hopefully that makes sense. Okay, so let's talk about heuristics. So the heuristic is the other part of this, G-score and H-score to make F-score. And there's a few characteristics that heuristics are supposed to have, quote unquote. One is that they are admissible. So admissible means that for every position XY, the heuristic of XY has to be less than or equal to the actual cost of getting to the goal. That's important, this less than or equal to actual cost for something to be admissible. The second characteristic that we might care about is consistency. So for every two positions, XY and a second XY, the absolute value of the difference between them must be less than or equal, again, to the actual cost of traversing between the two positions. Now, in like real search, in like real path planning, we want both of these characteristics to be true, because then A star is guaranteed to find us the optimal path, the best possible path. Now, in game AI, we don't really care. We don't care if it's both admissible and consistent. We don't care if it's either of those two things. What we care about is what it looks like. But if you can have them both be true, then A star will always find the optimal path. Cool? That's just a, there's fancy proofs we could look at, but this isn't the class for that. Okay, even with all of this, A star still has weaknesses. At worst, it can expand /open/check n squared nodes, where n is the number of locations in the world. This is especially bad for grids, right? Which is what you're going to be searching on or going to be applying this to. It can have a lot of grids nodes opened up. There are also stronger, more optimal forms of pathfinding. In fact, there's B and B star search. In fact, professors Nathan Sturdivant and Michael Burrow are world experts at pathfinding here at the University of Alberta, but they're much less commonly used in games. A star is still the most commonly pathing approach used in games. Okay. With that, we get to jump directly into assignment 2. Before I do that, is there any questions on any of this material? Just gonna click through it real quick. Why is A star called A star? Because there was an A and just an A pathfinding, and this one is a better one. Will we ever touch on B and B star? Nope, but there are classes here at the U Alberta that do touch on B and B star. So if you take particular classes from Mike Burrow or Nathan Sturdivant, they'll touch on B and B star. But we do not have the time to touch on them. Are they just harder to use and that's why they're less popular? I can't speculate as to exactly why they are less popular. One of the reasons is they're just not as well known, right? It's just a matter of precedent. People are used to A star in games, so people use A star in games. It is that they are in some ways more complicated. You have to think about path planning a little bit differently. Is A star similar to search algorithms like alpha beta? No, I mean, there's some comparison because pathing approaches and search approaches are similar, but in a search approach, you are typically searching for an entire answer. For pathing approaches, you are building up a path piece by piece as you go. Joel says, I'm confused how the heuristic is less than the actual cost of getting the goal. Less than or equal to, right? So for example, Joel, for a grids, we could use the Euclidean distance, the straight line distance, but we would know that in a grid, you can only actually move up and down and left and right and et cetera, which means that the Euclidean distance would be less than the actual cost of getting there. But also just consider the simple case of there's an obstacle in your way. So if we do like a Manhattan distance, straight line distance to the goal, right? We would say, hey, it might look like there's only 3 units we have to go to get to the goal, but actually we have to go all the way around an obstacle to do it. Does that make sense, Joel? Okay, cool. So with that, oh, one more. When we discuss graphs, are we allowing multiple edges between any two nodes? Is that why the pseudocode showed earlier that if else statement involved replacing paths? Adrian, yes. We are assuming there can be multiple edges between any two nodes. I mean, not just any two multiple edges between any two nodes. It might be that there's multiple, each node might connect to multiple other nodes. And because of that, you might end up with, weird paths, right? Because connections of multiple edges, not just a single edge connecting different nodes. But yes, that is possible in graphs to have multiple edges between two nodes. That is not the only reason you have this if else statement in replacing paths, but it is one of them. Okay. Here we go. So I'm going to do the typical thing, which is I am going to sort of talk you through this assignment. I'm not going to read it to you completely. Please do actually read the assignment. I had people asking questions which were just answered in the hint section of the assignment. So please read at least this section, if nothing else, right? But I'd recommend reading the whole thing. It's really going to help you. So again, your goal here is going to be to implement A* to be able to, help Pac-Man move through this grid a little bit more effectively. So you are going to be only interacting with one script in this assignment, even if you do or editing one script in this assignment, even if you do the extra credit. So you're only going to be changing A* pathfinder.cs. That means I only want you to submit A* pathfinder.cs, which means you should only make changes to A* pathfinder.cs. The script does make heavy use of A* node and priority queue.cs. In addition, you might find it helpful to look at graph node. Graph node is the parent of A* node. If I say that a class is the parent of another class, that's just something you should understand. And if you don't understand it, I would recommend looking up object-oriented programming and familiarizing yourself with the notion of classes and parenting and things like that. So our graph node is our basic representation. It's going to hold things like our location, the neighbors that it has. It has the ability to add a neighbor. You're not going to have to use that. Its hash code, etc. An A* node inherits from graph node, or actually just holds graph node. Sorry, it's my bad. It just holds a reference to graph node. It stores the location data. The A* node has a reference to its parent. This is a different version of parenting than what I was mentioning earlier. This is just what's the node that we got to, that we came from to get to this node, that we were at before coming to this node. This is helpful for putting together a path later. It has a reference to its own location, its G-score, H-score, and F-score. It also has a few functions. None of these are going to be particularly relevant to you, though you're going to need to instantiate A* nodes. So you'll have to look at that. Priority queue is your priority queue class that you get to use for this assignment. It's just given to you. I've given it to you ahead of time, and I've implemented it in a very particular way. We'll get to that in a second. Data is a read-only, as in you cannot make changes to it directly, list that reflects priority queue's internal list, okay? So this is important. You are not going to be able to make direct changes. You're not going to be able to directly reference or make changes like remove things to the list for priority queue. That's because of this need to keep things in order. So you do have an ability to do an NQ, which is adding an item to the priority queue, a DQ, which is the equivalent to pop, removes and return the minimum cost item from the queue, and a peek, which is going to return the minimum cost item in front of the queue, but does not remove it, just lets you see it. Then you'll get a count, which is just the size of the queue as an integer, and removes the specified item from the queue. So this is the way that you're going to have to do the replacement. You're going to have to use remove to do the replacement. All right, so some instructions. I've given you a gridhandler.cs file, but it is not generating grids on the fly. Instead, it is just baked in, says where all the grid cells are for the 5 maps that you're given. Some of the 5 maps are the same, some of them are different from assignment 1. Then you need to modify A* Pathfinder to complete calculate path, which is just literally implementing A*. You'll see it in just a second. You can, alternatively, for the extra credit, modify the heuristic function, which we'll take a look at in just a second, and then finally get to test your implementation. You can also always change the maps by modifying up to test points. Okay, let's get to the grading/marking in just a second. I'm going to actually just show you what this ding ding thing looks like. Let's go ahead and open it up. Maricel says, when we work on our assignments, are we expected to only use the functions and variables that are listed in the PDF? No, you can create your own functions and variables. What you can't do is import external libraries. Okay, taking a second to load. All righty, so let's take a look at this. So already, even just with this, we can see that scene 1 looks quite a bit different, right? If I click somewhere on the game view, not on the scene view, like here, you can see that down here at the bottom, it says checked 62 nodes. Seems reasonable. But let's say that I go to this top left corner of the map. Okay, and then I'm going to go to this, well, I got just 5,882 nodes, not great. And then if I hit the bottom right corner here, it's going to just fail. And on its way to failing, it will check 37,000 nodes. Not great. Let's jump back to this assignment PDF. You can see that the homework assignment is worth 10 points. Your solution will be graded by an autograder per the usual. The autograder will attempt to have Pac-Man navigate from various points across each map. I will not tell you those points. For every map that your solution is tested on, 1 point will be deducted if your implementation expands more nodes than is necessary if you did not implement A-star correctly. The autograder will test your solution on 10 maps, 5 provided and then 5 withheld. Same setup as assignment 1. For the given 5 scenes, going from the top left to the bottom right corner should lead to the following or fewer nodes being created with the default heuristic. So for example, in scene 1, doing this thing we just did, going from the top left to the bottom right corner, we should only expand 140 nodes in comparison to the 37,000 nodes and a half that we just did, right? I'll just show you this again, right? Come on, Pac-Man, you can do it. Get out of there. So if I do this again, where I say go to the bottom right corner, again, 37,574. So that's your goal. You're going to cut that number down to about 100. Scene 2 looks like this. It is largely unchanged from last time. I'm not going to do the same thing, but the number is also very large there. Scene 3 looks like this. Also largely unchanged from last time. Scene 4 looks like this, largely unchanged. And scene 5 looks like this, also largely unchanged. So scene 1 is the big new change, the one that's changed the most from assignment 1 to create this sort of like backwards L shape. Are the grids for assignment 2 valid for all the maps? Yes, because I've ensured that the default grids are valid. I will show you in just a second how this works. So here's my grid handler that I've given you. You can see here, it just literally prints every single position of every single grid for every single scene. So what you can do is copy and paste your grid code into here if you want, and then you'll have your grids. Doesn't matter. But that's just the default, just because there are people who aren't going to complete assignment 1 who still want to do assignment 2. Okay, so let's take a look at A-star Pathfinder, which is the default thing. We have to stop in about a minute for the practice quiz, but just to look at this real quick. So what it's doing right now is it is checking to see, hey, is the open set dot count greater than 0? This is just equivalent to the is it empty? I also have a maximum number of attempts, which is why I can just fail and try to straight line distance. Then we do attempts plus equal to 1. You don't necessarily need to keep this, but it might be helpful while you're developing this. Then we grab the current node. We check and see if we found the goal. If we did, we reconstruct a path. Then we want to check each neighbor. So we do the G-score, we figure that out. We grab the A-star node neighbor, we instantiate this A-star neighbor, and then we add it to the open set. And that's it. The things that are missing here are access to the closed set. Right now, there isn't a closed set at all. You're going to have to implement a closed set. However you want to do that is up to you. And there's not any of these checks, these very particular checks, right, that we were doing. So we aren't checking to see if it's in the closed set, obviously, because we don't have a closed set yet. We're not checking to see if it's already in the open set, and we're not doing the replacement. That's it. You might say like, oh, wow, that's like, what, 3 or 4 lines of code. It's going to take you a while. Trust me. Okay, and then the last thing is the heuristic. So the heuristic right now is right here. It is literally the Manhattan distance. So it's the absolute value difference between the X and the Y dimensions. That's it. The way that this, now let's talk about the extra credit points. So you can get up to 1 point of extra credit for implementing a better heuristic than the one currently implemented in heuristic, the Manhattan distance. The best student implementation in terms of fewest nodes explored, the instructor A* implementation, and any implementations of 10% of the best, within 10, that should say within 10% of the best, will receive 1 extra credit point. All other implementations will receive a fractional percentage based upon their relative performance, but at minimum, students will receive 0.1 extra credit points if they do better than the provided heuristic. Okay? Any questions on that? There's some hints here that we don't have time to go over today. Okay. If there's no immediate questions, wait, so only top 10% of people get 1 extra credit point? Kind of. This is sort of a competition. What I'll say is that everybody's going to get, if you do well on it, you will get close to 1 extra credit point, but only, you know, it's not 10%. It's people within 10%. Within 10% of the expanded nodes will get 1 extra credit point. But everybody's if you do well, you will get close to 1 extra credit point. If you do not so well, you won't do as well. This is the only one that's set up like this. Okay, with that, it is practice quiz time. I have thrown the practice quiz into there, and I'll also put it here in the general chat. Let's go ahead and open this up. 4 questions. Give you about 8 minutes, and then we'll really quickly go over the answers. If you do have general questions that don't reveal an answer, I'm happy to answer them. The quizzes are open everything but each other. Yes, but each other. So don't talk to each other during the quiz. I can't enforce this, right? But also the professors who are like, oh, don't look at your quiz on this, or don't look at your book during this online quiz, also can't enforce that unless they use weird invasive software, which I wouldn't use. But just please don't, chat with each other during the quiz. That's all I ask. But yeah, during the real quizzes, feel free to look at quizzes or look at, prior slides, look at your own notes that you've looked at. There's no book. We can look at assignments, etc. Yeah, I agree. It's weird. Like I have a weird, green screen up, so you don't get to see more of what my living situation. I would have no interest in trying to force you all to let me see your house. That's so weird. He says, even if you turn the camera on, you can totally still look at something behind the screen. For sure. Yeah, it's so easy to cheat it anyway. That's very silly to me. Student screen is watermarked by the name. No, I'm sorry. You can't get rid of the watermark. Yeah. The alternatives to the watermark are I make everybody have a password for the Zoom, which I don't want to do. I want it to just be a link that people can get it to, or I have to do a waiting room where I have to individually let people in. And also I don't want to do that. What if I stream on Twitch instead? No, I'd rather not. I know people who've gotten, talk about Zoom bombing. I know professors who've gotten, some real foul stuff happening to them on Twitch. All right. People are chatting a lot, which I assume means that people are feeling pretty good, or at least some of you are. Give it about another minute, and we'll talk about answers. Okay, let's go ahead and go through some answers. We'll probably go a little bit over time, so if you need to bounce, understandable, though it's not like you have to walk anywhere today, thankfully. Okay, number one, which of the following has the largest runtime memory cost, typically? Just throw me some letters in the chat. A, grid generated, B, nav mesh generated, C, path network authored, and D, these are roughly equivalent. I love to see all the A's. It's like the Fonz in here. Yes, so it's A, right? It has to be A. I've literally given you the answer to this on an earlier slide earlier this week. It's A. Grids have by far the most nodes and the most edges using the language we talked about today. Okay, number two, let's say you wanted to use one spatial representation for both environment A, which is and the B, which is on the right. The difference being, it's got circles and ovals versus rectangular prisms. Which one would you pick and why? Now, the trick here is, of course, that it depends entirely on the why. That's not entirely true. You would really want to say you'd either want to go with a nav mesh or you'd want to go with a path network here. A grid would be hard to say would be the best fit for A because of these rounded edges, right? Because of the rounded edges and the fact that a grid is little cubes or little squares, you're not going to be able to do a very good job of filling the space. So a grid, you'd have to give me a really good reason why it has to be a grid. But for a path network or a nav mesh, right, you could say either of them makes sense. For nav mesh, you might say, okay, we have more area because there's big open areas on both maps that we would like to walk around freely. For a path network, you might say, okay, we're constrained, right, in certain ways. And so a path network, or in certain areas, and so a path network might make the most sense. Plus, you can then just go a little bit off the path network, right, and that'll allow you to get coverage over all these regions. Answers like this, there's more on the next slide. All of those would be good. Question 3, what particular implementation details would be important to your answer for 2? E.g., what would you have to do to make sure it worked for both? So if you use a nav mesh, for example, the way that we talked about generating a nav mesh was about using points, right? Using points to be able to build up your nav mesh. So if we have ovals and circles, there are no points, right? There's no edges to these. And so to get around that, we would have to basically surround these ovals with many sided polygons to be able to approximate that and to be able to make use of the space, or to change our generation approach for a nav mesh entirely so that we could make use of more sort of spherical spaces like this. For a path network, it would be about sort of the distance that you would allow for travel off of the path network. If you're using a flood fill algorithm or something like that, it would be about sort of how far off you could have the various neighbors of your flood fill be. Finally, what steering approaches would you use for a gang of chaotic motorcyclist enemies in a video game? So because we're talking about a gang, we're talking about a group, it makes sense to use some of the things that we talked about for voids, like separation and cohesion. But if we use just those, if we just said separation and cohesion, because we're talking about a gang of group, we would end up with something that looked way too beautiful and flowing for a motorcycle gang. Not saying that they can't be, but if they're chaotic motorcycle enemies, we probably want them to a little bit harsher than that. So we can use something like kinematic wander or something like that to give it a little bit of roughness, right? To give it a sort of a little bit more random speed ups, a little bit more chaos in the system, right? Something like that. Other answers would be fine here too, but I'd really be looking for 2 things. One, for some notion of how you could steer the group, right? And a second, a way that you could represent this chaotic motorcycle enemy sort of characteristic. So I would probably give you half points if this was a real quiz, David, if you answered with just the separation. That would not be sufficient. Because if it was just separation, right, they eventually just get pushed so far away from each other, just a diffuse across the map. Okay, cool. Some questions. I'll stick it around for a few minutes to answer some questions in the chat, but otherwise you're free to bounce. If I picked a hand tweak path network for Q2, would it be acceptable answer that I picked it specifically to avoid implementation consideration for Q3? Unfortunately not, Ohi, because hand tweak path networks, there are still parameters you have to tune, like the distance you're allowed to travel off the grid, or sorry, off the path network and things like that. Could I have put pursue route? So Jin, it wouldn't really make sense for question 4 to put pursue route because there's not talking about anything that they're pursuing. Now, if you gave me some extra detail to say oh, I'm going to assume that they're enemies, they're going to be pursuing the player, then sure, bringing up pursuing would totally make sense. Okay. Any other questions? All right, I think we are out of questions. I will stick around till people feel free to leave. I'll stick around until there's 10 people left in the chat, and then just in case there are last minute questions, and then I'll stop the recording. Thanks all. Have a good Friday. When will you go over assignment 1? I will not go over assignment 1, Maristella. You'll not get the answers for assignment 1. You will get feedback on your submission for assignment 1. And if you want, you can have a one-on-one chat with me about your particular assignment, but I'm not going to give the answer for any of the assignments. Otherwise, it would break, the setup of this class. There's also not just one answer for like any of these assignments, except for maybe assignment 2. Olivier, you say, I'm a bit confused about the answer to Q3 if we chose path networks in Q2. So path networks, even hand-designed, hand-tweaked path networks, right? They're still going to have some parameters, which are going to be implementation details, right? So even if it's the case that we would say like, okay, I want a node, here and 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 here, right? We would still have to pick things like how far off are we going to let a NPC get off of this path network, right? That's a parameter we would have to choose. And that's a choice we're making, and therefore it's an implementation detail. Does that make sense? Marisol says, so after the A1 submission due date, can I go to office hours to ask about the extra credit? Sure. He says, will we, after it's submitted, be able to discuss our solutions results in the assignment 1 with other students in the class? You can discuss them, but I would ask that you not share code still. Please don't share code at any point. Yagi says, what can we do if the grid doesn't cover the very bottom of the assignment run 1? I have no idea what you could be talking about there. It sounds like your for loop is messed up in some way. Or maybe the choice of X and Y that you're using somewhere in your code. I would say come to office hours. That will be in 4 minutes. It'll be on a Google Meet link that I'll put in the Discord. We can talk about it there. Assignment 2 is open now. Yeah, it's on eClass. You cannot download the files. What? I don't know what that means. That might just be a web browser issue, because your web browser won't let you download the files. Is anybody else not able to download assignment 2 files? Shoot me an email, Naheen. The files cannot be found? Shoot me an email. I can just directly send you stuff. I'll double check the eClass as well in a few minutes before I'll be online. Okay, I'm going to stop the recording there. Bye all.